Hello students, today we are going to start with the first part of electrochemistry, in which we are going to discuss certain basic concepts like oxidation, reduction, methods of balancing chemical equations, electrochemical cell, half cells, electrodes, electrochemical series, types of electrochemical cells, types of batteries, and various other related concepts. Let's start with electrochemistry itself. English scientists John Daniel and Michael Faraday are credited as the founders of this branch of chemistry. We can define electrochemistry, that branch of chemistry which deals with the relationship between electrical energy and chemical energy and the interconversion of one form into another form. Electrochemistry is based on the concept that flow of electricity through a substance may induce a chemical change in the substance. Similarly, a chemical change may cause a flow of electricity through some external circuit. The next term is oxidation. The process which involves addition of oxygen or loss of electrons or increase in the oxidation number of an atomic system can be defined as oxidation. Another process is reduction, which involves gain of hydrogen or gain of electrons or decrease in the oxidation number of an atomic system. We must keep in mind that oxidation and reduction are complementary processes. None of them can take place in an isolated way. They take place side by side. Since oxidation and reduction are complementary processes, that means that if one of the species is getting oxidized, some other species is getting reduced with it. It gives us another term, redox reaction. So redox reaction can be defined as a chemical reaction which involves oxidation and reduction. So let's take the example of copper ions and zinc. In this reaction, copper ions are getting reduced to copper, whereas zinc is getting oxidized to zinc ions. So the oxidation half is the oxidation of zinc into zinc ions, and the reduction half in this reaction is the reduction of copper ions into copper. A redox reaction always involves transfer of electrons from the reducing agent to the oxidizing agent. Now we get two more terms. One is the reducing agent and the other is oxidizing agent. Let's see what are they. So the oxidizing agent can be defined as the species which gets reduced in a reaction, oxidizing the other species. So in this reaction, copper ions are the oxidizing agent because they are oxidizing zinc into zinc ions, and in this process they themselves are getting reduced to copper. Similarly, reducing agent is that species which gets oxidized in a redox reaction, reducing the other species. So in this redox reaction, zinc is the reducing agent since it is reducing copper ions into copper and it itself is getting oxidized into zinc ions. The redox reaction that we just discussed was very simple reaction and perfectly balanced as well. But we must know how to balance a given skeletal redox reaction. One approach is the hit and miss approach, but it can be done in a systematic way as well. So there are two methods for that purpose. First is the oxidation state method and the second is ion-electron method. Let's see what are the various steps involved in these methods. The first method is the oxidation state method proposed by Johnson. In this method, the first step is to write the skeletal equation for the chemical change taking place. Then oxidation numbers to the reactants and the products are assigned. The change in the oxidation state is determined for the oxidation and the reaction half. This change in oxidation numbers is then equalized by multiplying with a suitable coefficient if required. Substances other than hydrogen and oxygen are balanced in the reaction by multiplying with a suitable number if required. Then the oxygen atoms are balanced by adding water molecules to the deficient side. For balancing the hydrogen atoms, in case the chemical reaction is taking place in an acidic medium, hydrogen ions are added to the deficient side. But in case the chemical change is taking place in basic medium, the hydrogen atoms are balanced by adding water molecules to the deficient side and hydroxyl ions to the other side. This method will become more clear to us once we discuss an example. Let's take this example. We have to balance this given equation. So first of all, we'll assign oxidation number to all the elements involved in the reaction. In HNO3, the oxidation number of hydrogen is +1. We already know how to assign the oxidation numbers. That of nitrogen is +5 and that of oxygen is -2. Of iodine is 0. Again, hydrogen is +1. Oxidation number of iodine in HiO3 is +5 and of oxygen is -2. In NO2, the oxidation number of nitrogen is +4 and that of oxygen is -2. In water, oxidation number of hydrogen is +1 and of oxygen is -2. Now first of all, let's consider the oxidation reaction that is taking place. This is the oxidation reaction that is taking place. As we can see, the oxidation number of iodine is increasing. Therefore, this is an oxidation reaction. The oxidation number of iodine in I2 is 0 and of HiO3 is +5. So the change in oxidation state for iodine will be 0 minus 2 into +5. Since there are 2 iodine atoms, this will be equal to 0 minus 10, that is -10. -10 is the change in the oxidation state. Now let's have a look at the reduction. HNO3 is getting converted into NO2. The oxidation number of nitrogen in HNO3 is +5 and that of nitrogen in NO2 is +4. As you can see, the oxidation number of nitrogen is decreasing. Therefore, this is the reduction reaction. So the change in the oxidation state will be +5 minus +4. That is equal to 1. Now for balancing the change in the oxidation state, we are going to multiply the reduction half with 10 and the oxidation half with 1. So we'll get the equation 10 HNO3 plus I2 gives 2 HiO3 plus 10 NO2 plus H2O. Now the elements other than hydrogen and oxygen involved in this reaction are nitrogen and iodine. So first of all, let's check for nitrogen whether the nitrogen atoms are balanced or not. On this side of the arrow, that is the left side, we have got 10 nitrogen atoms, and on the other side as well there are 10 nitrogen atoms. So nitrogen is balanced. Now let's look out for iodine. On the left hand side there are 2 iodine atoms, and on the right hand side also there are 2 iodine atoms. Therefore, iodine is also balanced. Now let's balance the oxygen atoms. 10 into 3, that is 30 oxygen atoms are present on this side, whereas on this side there are 3 into 2, that is 6. 6 plus 10 into 2, that is 20. That gives us 26 plus 1, 27. There are 27 oxygen atoms. So the right hand side is deficient of oxygen atoms. So for that case, we are going to add water molecules to the deficient side, that is the right hand side. So on adding 3 water molecules to the deficient side, we get 2 HiO3 plus 10 NO2 plus H2O. This is the same equation as above. Since this side requires 3 more oxygen atoms, we are going to add 3 more water molecules to it. Or we can write 10 HNO3 plus I2 will give 2 HiO3 plus 10 NO2. On adding these water molecules, we can simply write 4 H2O. So after oxygen atoms, let's check out for hydrogen atoms. This side has 10 hydrogen atoms and this side has 2 plus 4 into 2, that is 8. 8 plus 2, 10. So now this equation is our perfectly balanced chemical equation. That is 10HNO3 plus I2 gives 2HIO3 plus 10NO2 plus 4H2O. The second method is the ion-electron method proposed by Jet and Lameo. In this method, the chemical equation is split into two halves, the oxidation half and the reduction half, by putting the appropriate number of electrons involved in the chemical change. Then we balance the atoms other than oxygen and hydrogen in the two halves by multiplying with suitable coefficients if required. Then we balance the oxygen atoms by adding water molecules to the deficient side. For balancing the hydrogen atoms, in case the chemical change is taking place in the acidic medium, we add hydrogen ions to the deficient side. And for basic medium, we add water molecules to the deficient side and hydroxyl ions to the other side. Then the charge in the half reactions are equalized by adding electrons. And ultimately, the two half reactions are added to obtain completely balanced chemical equation. Let's take an example to clarify this method. Now we have to balance this redox reaction using the ion-electron method. So the first step is to split this reaction into two half reactions, one for oxidation and the other for reduction. This is the one half. MnO4 minus gets converted into Mn2 plus, and the other half is Fe2 plus getting converted into Fe3 plus. This is the oxidation half and this is the reduction half. So first of all, we'll balance the oxygen atoms. In this half reaction, there are 4 oxygen atoms given on the left hand side but none on the right hand side. So we are going to add 4 water molecules to the deficient side, that is the right hand side. On adding water molecules, we can write MnO4 minus gives Mn2 plus 4H2O. There are no oxygen atoms in this half reaction, so they are not required any balancing. Now let's count the hydrogen atoms. There are 4 into 2, that is 8 hydrogen atoms present on the right hand side but none on the left hand side. We can see that this reaction is taking place in the acidic medium, therefore we are going to add hydrogen ions to the deficient side, that is the left hand side. So on adding 8 hydrogen ions to the left hand side, this is the equation we get. Again, there are no hydrogen atoms in this half reaction, so they do not require any balancing. The next step is to equalize the charge. The charge on the left hand side is -1 plus 8H plus. That is -1 plus 8. We'll get plus 7. And on this the charge is of course plus 2. So we are going to add 5 electrons to the left hand side to equalize the charge. So the reaction will be MnO4 minus plus 8H plus 5 electrons will give Mn2 plus 4H2O. Now here the charge is plus 2 on left hand side and plus 3 on right hand side. So we are going to add 1 electron to the right hand side. So the equation that we get is Fe2 plus will give Fe3 plus an electron. Now since there are 5 electrons in this half reaction and 1 in that, for equalizing their numbers in both, we are going to multiply this half reaction with the coefficient 5. So we get 5 Fe2 plus, we give 5 Fe3 plus 5 electrons. Now we are going to add the half reactions. On adding the half reactions, first of all let's write the left hand side, which is MnO4 minus plus 8H plus 5 electrons plus 5 Fe2 plus. Now let's write the right hand side of both the reactions. It is Mn2 plus 4H2O plus 5 Fe3 plus 5 electrons. These 5 electrons will get cancelled. Since there are no other common species to be cancelled any further, our final equation will be MnO4 minus plus 8H plus 5 Fe2 plus will give Mn2 plus 4H2O plus 5 Fe3 plus. This is our final balanced chemical equation.